Welcome everybody to today's webinar presentation. My name is TJ Willits with Veolia Water Technologies. Before we begin, I'm just noticing that there's still a lot of people signing in. So to allow them to take advantage of the webinar, we're just gonna give them a few more minutes to get settled in before we start the presentation. So thank you for your patience. We'll begin in just a few moments. And for those that may have just signed on, we're just going to give just a few more moments to allow some of the other people that are logging on now to get settled into the presentation. So thank you for your patience. Okay, we're going to get started. Again, my name is TJ Willits with Veolia Water Technologies, and I want to welcome you to today's webinar presentation entitled Maximizing TSS and Fog Removal while Reducing Associated Sludge Disposal Costs Using the Unique GEM Flotation Thickener System. Just a few housekeeping slides before we begin. Obviously, many of you are likely hearing me. If you are having some audio issues, there's two main ways to connect to the audio. You could use your computer audio or headphones, or you could call in using a telephone, a landline or cell phone. If you're having audio issues, just go ahead and maybe toggle to the other option and dial in if you're having any issues, and that normally clears everything up. Due to the large number of attendees for today's webinar presentation, everyone's microphones are automatically muted. Even though your microphones are muted, we really wanted to make this an interactive presentation. To do so, we have enabled the question panel that can be found on the right-hand side of your screen. Throughout the presentation, if you have a question, go ahead and submit it in that question box. And the goal is after the main presentation, we'll get to as many of those questions as possible. And this webinar is actually part of a large webinar series that has started all the way back in April and continued through May. There's a few more webinars left in this particular series. If you wanted to go and browse some of the other upcoming webinars, you can visit our website at veoliawatertech.com. The address is there at the bottom of your screen, and you can sign up for those future webinars. In addition to those live webinars that we have left, we also have released all of our previously recorded webinars. We're up to at least 40 or so on-demand webinars that you could watch as well. And again, you could visit our website, veoliawatertech.com, and you'll see a button on that website where you could go and browse all the various content that we have, and you can watch it 24/7. And part of this webinar series, if you attend the webinar, you will receive a PDF participation certificate. These are normally emailed a day or so after the live presentation or after you view that presentation online. So be on the lookout for that. Maybe check your spam folder if you don't see it within a day or two. And something fun that we're doing is that we really value the feedback from you on these live presentations. We're always looking to improve and enhance and find new topics to discuss. So at the end of the webinar, you'll be presented with a chance to take a survey. It only takes a few short moments, and it'll help us make that content better in the future. And as a little bit of thank you, we're going to put everyone who completes the survey into a drawing to receive a $25 Amazon gift card. So Thank you in advance for just taking those few moments to provide a little bit of feedback. Okay, and just before we start today's presentation, a little bit about Veolia Water Technologies. As we're a global water treatment specialist, we focus in three key main areas, and that's providing technologies, bundling projects, and providing services to customers for industrial and municipal types of customers. And to introduce our expert panelists for today, with us today we have Daniel Lamar, a process engineer at Veolia Water Technologies. Danielle graduated from École Polytechnique in Montreal and received a degree in chemical engineering, as well as a master's degree in environmental sciences from Polytechnique. Since graduating, Daniel worked in the biopharmaceutical field, as well as for different water treatment system manufacturers. During his career, this led him to work both in drinking water and wastewater applications for both municipal and industrial clients. His position brings him with some key areas such as R&D, taking new technologies and introduce them to the market, as well as process engineering on some very advanced full-scale projects. And since Daniel, he's been working currently at Veolia for the last 20 years as a process engineer and is a true expert in this project, in this type of technology. So with us, Daniel, are you here?
Yes, I am. Hi, everybody. Okay, so today's presentation is starting with the GEM system. Just me get control here. There we go. We are so with the agenda. So we'll go quite fast over what's a DAF system to try to get a comparison between what's a general traditional DAF system and what's different with the GEM flotation system, which is similar to some extent, but also very different in some other ways. And then go through sludge thickening, what can be done in terms of sludge handling with the GEM system. Then a few case study. It's always good to know how this technology can be applied in full scale and in real life, and then a little wrap up. So the GEM system can be applied typically in food and beverage industry, can be applied in many other industries, but it's a prime technology for food and beverage applications, mainly where effluents contain significant amount of FOG and TSS, which is basically where a traditional DAF system is used. The system can be used as a standalone or upstream of biological treatment. So standalone, usually used for pre-treatment before sewer discharge. And with biological treatment downstream, usually if final effluent needs to go to the environment. Sweet spot, of course, as I mentioned, when there's lots of FOG and TSS. So the higher the concentration, the best the GEM is for that application, always when comparing to other treatment options on the market. It's very good application, also where the sludge disposal costs are relatively high, because one of the main characteristics of the GEM system is its ability to generate dry sludge, dry final sludge, which does reduce the sludge disposal costs at the end. So typical markets, I would say almost all of the food and beverage market, well, probably less in the beverage where the effluent is more soluble based, but as soon as you start getting TSS and especially FOG and TSS, then you're getting more and more in the sweet spot. So dairy industry, meat and poultry, of course, and then all of the others. So just a short summary of what's a standard DAF technology as it's used to do a comparison between the GEM system. So as you probably all know, that DAF technology is really dissolved air flotation. So the goal is to separate solids, and FOG, fat, oil, and grease is considered more or less as a suspended solid. So FOG and TSS together can be attached to micro bubbles, and this clump of particle floats to the surface, and then that float is skimmed off from the surface using a surface scraper, and that is sent as a waste sludge, and then the treated effluent leaves from the bottom of this flotation tank as treated effluent. Now, the driving force on a traditional DAF system is really this white water. So you need these micro bubbles to get the flotation of the solids. And how do you generate micro bubbles is to recirculate some of the treated effluent, pressurize it to a few bars, 6, 7, 8 bars typically, and then put that water stream in contact with pressurized air and dissolve that air into this high pressure water. And then once you drop down the pressure to ambient atmospheric pressure, then you will generate these micro bubbles. And this actually visually is seen as white water. It just becomes white, just like when you open the tap at 2 o'clock in the morning. Sometimes the water, your glass of water turns white. So it's similar to this. It's tiny air bubbles that will attach to the solids. And that the DAF system, of course, will give you better results if you add chemical conditioning upstream of the system. So coagulation and flocculation will generate larger flux and will improve the removal rates. So looking now at the GEM system, how it is similar and how it is different from a DAF, a traditional conventional DAF system. So we can say that the GEM system is really a second generation dissolved air flotation system, while the conventional DAFs have been around for decades. The GEM system is not the new kids on the block, but it's still newer than the DAF system. And it is very efficient, providing, in terms of pollutant removal, providing FOG removal usually better than 98%, and TSS 95% plus. So that's one of the first advantage of the GEM system as compared to a DAF, the very high efficiency. While you would normally see something like 90% removal with the conventional DAF system. So super high pollutant removal efficiency. Then the GEM, as written everywhere in the in this presentation, even from the head title, does generate a drier sludge than any other DAF system on the market, and that will allow significant savings when in terms of sludge disposal costs. Then it's also very compact, and compactness, while not being usually a game changer, does provide significant benefits, usually when a new building construction is involved, or even when trying to install a new treatment system within an existing building. So compacity can be a big something if a footprint is an issue. And then I was mentioning it, the GEM is not the new kid on the block, because there's lots of references, more than 500 in the world. It's been around for a good 15 years. So you were not starting from R&D and from scratch here. It's fully proven in many different markets. Looking a little bit on differences in terms of operation between conventional DAF and the GEM. The conventional DAF generates this white water, and as mentioned earlier, it's using a recirculation stream. Typically between 10 and 30% of the influent flow is recirculated as white water flow, and that increases the hydraulic load on the separation tank. So that is one of the reasons why a conventional DAF system is larger. And also these DAFs are usually more mass load design, which means that the higher the pollutant load, the larger usually the DAF system is. On the other side, when you consider the GEM system, one big difference between the conventional DAF is that you don't have this recirculation stream, but rather you pressurize 100% of the feed flow to a typical, similar pressure than a conventional DAF. So we're talking 6-7 bars maybe. And then sending pressurized air, compressed air, into this 100% of the feed flow. So the white water production is very significant as it's done on 100% of the feed flow. But having no recirculation, the tank is smaller. And then the system can handle lots and lots of pollutant loads, which means that most of the GEM systems are flow-based design, with the pollutant loads having marginal impact on the final design, apart from chemical consumption and sludge production. So what happens within the GEM system? So if we follow the drop of water through these 5 steps, the first step will be coagulant injection, so similar to conventional DAF. So you need to do your chemical conditioning, but here only the coagulant injection. So coagulation is done upstream, so usually upstream of the feed pump, as far upstream as you can. You can never have enough of the coagulation tank or too much coagulation tank time anyway. So as upstream as you can, coagulant injection, just similar to any DAF system. Then the water goes through the feed pump, which is mounted here below the GEM unit. So 100% of the feed flow gets pumped and pressurized. And then the water goes through a series of mixing heads that we have here, which is showing 5 to 6 heads, depending on the model of the GEM system. And several things happen within these heads. So within the first few heads, we have compressed air injection, and the goal is to dissolve air into 100% of the feed flow. And once this is done, after going through the first 2 or 3 heads, then through each of these mixing heads, there's a pressure drop. So as the pressure drops, you're starting to generate some micro bubbles that will be used a little later to float the solids in the separation tank. And then we're adding polymer. So there is injection of 2 polymers, usually one anionic, one cationic. And in these mixing heads, there's also stretching of the polymer macromolecules, which will allow creation of a struck flux and microbubbles captured within the flux. And we will see this a little more in detail in the next slide. So once, after going through all of these mixing heads, the mixture of liquid and flux that were formed in the heads are just injected in the separation zone, which is similar to any conventional DAF. So in that tank, you just have flotation of solids and a skimming of the floats, and then the discharge of the treated effluent from the bottom. And then the final sludge from the sludge hopper is pumped with the pre-installed sludge pump and sent to whatever disposal or further thickening. So we will come back to the thickening part a little later. So what really happens in the GEM system as compared to the conventional DAF, and that explains some of the performance that can be obtained in the GEM system. So going a little behind of what can be experienced in the DAF, in the conventional DAF, this process is really driven by a collision approach, where the goal is to create these large flux using polymer, using coagulant. You have the solids, FOG, all of these attached together and form one big flock. And then this is injected in a tank where you will inject at the same time micro bubbles from the whitewater recycle loop. And these micro bubbles will attach to the periphery, to the external part of the flux. And then this flux is loaded with micro bubbles. It will float up to the top of the separation tank and will be skimmed off. What you see in this picture, all the black dots here are water molecules or water droplets that are all captured within the flux, and which is one of the reasons the float solids is somehow watery. And this is different from the gem. So in the gem system, we're starting with a polymer backbone, which is this shown here as one big polymer. So the polymer used in the gem system is a macropolymer, a very large polymer molecule. And what you want to do in one of the mixing heads is to uncoil this polymer strand. And once it's uncoiled, attach the coagulated flux, microflux, attach it to the polymer strand. And then as the water droplet leaves the mixing heads, the polymer strand will begin to recoil on itself. So, and then the air bubbles are attached within the polymer, well, within the flux actually, along the polymer backbone, which we have here. So we see in this picture the same components. So we see micro air bubbles, which are the blue dots here. We have the black dots, which are the water molecules. So we're generating a flux which is somehow different. Now the air bubbles are everywhere within the flux that was formed. And then once you release the pressure and inject this flux in the separation zone, well, the micro bubbles that were generated at a few bars are now expanding because you're releasing pressure. And as they expand, the air bubbles are actually pushing the water droplets out of the flux. And that's one of the reasons the generated flux and the generating solid sludge will be drier with the gem system than with the conventional DAF system. So basically, it's really the way that the flux and solids are generated, which are quite different between the two technologies. So and then afterwards, as the polymer backbone recoils, it will add additional forces on the flux, which will again push more and more water out of the flux themselves. And as you take these flux and let them quiescent within a static tank, the water will keep getting out of the flux just with time, with the pressure from the water bubbles that are expanding and from the polymer backbone that is recoiling. So just time will allow the water droplets to be pushed out of the water flux, of the solids flux. So while the DAF solid floats is typically 2 to 5%, in the GEM system, directly out of the GEM unit before any further thickening, 8 to 10% is easily experienced. Which brings us to the sludge thickening part. And as I just mentioned, the sludge thickening is very easy with this GEM floats because the flux that are generated are very strong and will float for weeks if you let them float on top of a static tank. So the idea to thicken further the GEM solids is to do exactly this, to let the solids stay settled, well, stay in a static tank, and leave them there for a few hours to a few days. And just by the action of the air bubbles and the polymer recoiling, the watering will happen by itself without using a costly centrifuge, for example. And this will generate this drier sludge, which we see here, which is one example. This one was probably 35% out of a dairy application. So the thickener itself is just a gravity thickener. It's actually a conical shaped tank, plastic tank that we use. The float is just pumped into the static tank. The thickened solid just float on top of the water here, and a clear water phase is generated at the bottom. You can remove the water phase from time to time. Usually this tank is operated in a batch mode, and then you are concentrating the solids, the floating solids, more and more until your tank is mostly full of thickened solids, and then you can pump out the solids. So these solids are still pumpable up to a very high solids concentration. So we usually use a PC pump to pump the solids to the final receiving bin. Typical design parameter for this tank, 24 to 48 hour retention. As I mentioned, the flux are very stable and will not break as the flux of a standard DAF would after a few hours. So these flux are stable for weeks. If you put them in a beaker, they will still be there in several weeks. So the goal is to create a liquid under natant, which is usually returned to the EQ tank for reprocessing through the gem. And of course, the number one goal is to create a very dense supernatant, which is the thickened sludge. So we're expecting usually 15 to 25% plus solids concentration. That depends greatly on which application. Usually the higher the FOG content, the higher the sludge concentration. And we did measure up to 45% at one occasion on a dairy effluent. Of course, the impact of getting drier sludge is really in the sludge disposal cost. So let's take as an example a dairy application that we did in Canada, designed for a flow of 2,400 meter cubes a day. The gem sludge dryness after thickening that was measured in piloting was 22%. That was after about 12 hours of thickening. The conventional DAF system would provide a dryness of 5%, and considering a sludge disposal cost of $50 per meter cube, the savings generated by the GEM system were $680,000 yearly, just on sludge disposal cost. There is thus a clear benefit in trying to generate as dry as possible a final sludge. The gravity thickening, why does it work so good? We did mention about the way the flux are formed. There's another few tricks in there. One of them being the use of an organic coagulant. So in most applications, we try to use this organic coagulant, which will not generate any hydroxides, which come with some linked water, which is very difficult to dewater. In some applications, metal salts are mandatory. For example, in meat processing applications, we usually will use some ferric to some extent, and then and that tends to generate more watery float. But as much as we can, we try to use organic coagulant, which will bring the thicker sludge. Also, the air injection in 100% of the feed flow is important. And of course, the use of the two polymers, as explained earlier, makes most of the difference. Just to tell you that the sludge is very stable. It can remain there for days and weeks. You can even mechanically stir the sludge, and we tried it. And you think that you break the sludge and the flux, and you think that the sludge will get more and more watery, but even if you mechanically stir, let's say with a paint mixer in a 5-gallon bucket, you can't manage to break it, and after a few minutes it will just go back to its original characteristics. So one comment that we get that we had at one point from one end user is that he actually had to adjust his polymer dosage, which means reducing polymer dosage, because the final sludge was just too thick for what his final disposal route was asking him to. So this is usually good when you can end up with very, very thick solids, even too thick for your final disposal. So you can always adjust the final sludge concentration, as mentioned here, by just reducing usually one or the two polymer dosage concentration. Does it work with any effluent? Well, most of them. So here's a few of the jar tests that we can do on several different applications. Most of them are quite rich in oil and greases, but not all of them. Even the candy applications did work great. Slaughterhouse, lots of TKN in there, lots of meat of blood, and in order to break the blood emulsion, you do need some iron. So adding some ferric with or without the organic coagulant usually provides excellent results. And then one of the characteristics that you see from running some jar tests, so these are all jar tests that we run in-house in our lab, is when you do the GEM system lab test, you end up with this clear water and the very thick clump of solids, which is quite representative of a GEM system operation. And then if you use the same wastewater and do a conventional DAF system lab test, you will end up with one thick layer of sludge, but it remains a layer, not a big, thick, not a thick clump as shown in all of these GEM system applications. So that's the first indication that the final sludge is quite thick and concentrated. So a few examples of performance that are typically encountered with the GEM system. As I mentioned earlier briefly, 98% plus for FOG removal and 95% plus for TSS. Of course, this is the final performance is case specific and depends on many factors, but as you can see here, oil and grease removal, we're talking 90% here because there wasn't that much oil and grease at the beginning, but then 90, 95, 99, 97, and then in the TSS removal, it's mostly 95% plus removal. So excellent removal, and then the COD removal, which is associated with the removal of the TSS and oil and grease. Of course, we're not removing the soluble fraction of the COD, but everything that's linked with particulate and TSS and oil and grease is removed, of course, with the GEM system. So all that being said, let's say you have one potential project in mind, want to know if your effluent is treatable and what kind of results you could expect by the GEM system. The pathway is quite simple. First off, based on our experience, we know more or less which applications are good and which aren't for the GEM system. Mostly in the food and the beverage market, most applications are quite well suited to the GEM system. And then the first step would be for you to send us a sample so we can run a jar test, which can be quite can be used to predict the chemical dosage requirements for coagulant and polymer, and of course predict the performance for TSS, FOG removal, and others if you have other objectives in mind. And so these can be run quite fast within 24 to 48 hours. And so just contact us and we will provide you with the sampling methods and everything. One thing that this lab test does not do is it cannot be used to predict the final sludge dryness after gravity thickening, because the sample volumes are just too small. We would need to do several, let's say 50 of these jar tests and capture all of the floating solids together to get a significant thick sludge volume that could be representative. So we try not to use these to predict the dryness of the sludge. And if that becomes very important, then we can, of course, the first thing we do is to look at our reference list and see which application is similar to yours to predict what's the expected final sludge concentration. If that needs to be proven, then of course we can mobilize our mobile unit. So we have one full-scale industrial unit, which is a GEM 30 model, which is treating up to 30 GPM. This one is mounted in a container, so ready to be used. This one can be rented for either pilot testing or rental if it's for actual treatment of an effluent, and it could be rented for months, or a pilot test could be conducted for typically 1 week to 2 weeks maximum, just to predict all of the parameters in real life applications. So seeing all the variations that a true production facility will generate during 1 or 2 weeks. Now some case studies. First one is the dairy industry. It's a large milk processing plant present throughout, it's actually worldwide, this one. The client need is, at this point, was they were operating an activated sludge without any pre-treatment upstream. So the activated sludge was receiving way too much organic load and was actually suffocating, even though they were injecting lots and lots of process air in the activated sludge. That was also generating a significant sludge management problem. So when they contacted us, of course, we came back to them, telling them the first thing they should do is to think of a pre-treatment upstream of their activated sludge. The water characteristics here, 800 more of suspended solids and about 500 milligrams per liter. So lots of FOG, which is typical for the dairy industry, which also make this kind of industry a very good market for, and very good application, I would say, for the GEM system. So the solution for them was a GEM system treating 100 meter cubes per hour. So they're 2,400 meter cubes a day. And the pilot test performance, further confirmed by the full-scale installation, showed 94% TSS removal and 99% FOG removal. And these removal were linked with removal of the associated COD, so up to 40 milligrams per liter, 40% removal of the COD, which made a very big difference on the downstream activated sludge. And the sludge dryness here was actually incredible, 35 to 47%. So you can see in the final bin what this final cake looked like. So it's mainly FOG from fat, oil, and grease from the milk processing activities. It actually looks like curd at the end, so it's very, very dry. The reason this industry went for a GEM system rather than a conventional DAF, even though the DAF would have provided a very significant removal of FOG and TSS, while there was an economical reason behind it as well. The GEM system, when comparing operating costs, was offering significant savings. If you were to just compare a conventional DAF with a GEM system, with the DAF generating this just the float sent to disposal, so this 3-4% solid sludge sent to disposal without any dewatering, then there would be a very significant difference in operating cost. It's made it at about $1.2 million a year. Then, of course, nobody would send this very diluted float to disposal. So when adding a centrifuge to dewater the DAF, the conventional DAF sludge, the DAF sludge volume was reduced significantly, which did reduce the sludge disposal costs, which was almost $1 million here per year. So that was reduced significantly, but still the delta was more than $600,000 a year between the two options. And then in terms of capital cost, the cost of the sludge dewatering system needed to be added, which means the sludge holding tank, which means the sludge feed solids pump to the centrifuge system, the polymer system, the conveyor system, and then the building to house all of this dewatering system. So based on these results here of the savings that were potential with the GEM system, this plant decided to go with the GEM system. Another application is a potato product processing plant. So this client is manufacturing French fries and other potato products. So it's starting really from the bare potato, so including peeling activities down to the final product, including bagging. That, of course, includes generating an effluent with lots of FOG, mainly from the French fries production, but also lots of TSS from all the peeling and potato cutting activities. This client is discharging its wastewater to the sewer system, so needed a pretreatment to meet the sewer discharge requirement. The objective was removal of TSS oil and grease, also pH adjustment. Flow was significant, 4,500 meter cubes a day for a Canadian-based company. This is quite large. And the goal, of course, was to minimize, well, not just sludge disposal costs as written here, but all of the costs, the whole life of ownership, cost of ownership during the life of the project. The conventional solution this client had in mind was to have equalization, actually two different equalization streams, because one stream was the oily wastewater that would go through a conventional DAF system, and then the starch effluent would go to a lamella clarifier, and then these two sludge would combine together to a centrifuge, and then sludge to disposal. Our solution was an alternative because it was based on using just a GEM system to do everything on the mixed effluent, which made things actually much simpler for the client to handle with a single equalization tank and a single treatment train. We did some lab tests on a few different samples that were sent to us from different operation activities in the production plant. And then a pilot was sent on site to confirm these. And the pilot results, as shown here, show almost 99% removal of FOG and 94% for TSS removal. So similar to what we usually see with the GEM system. What was also very neat for them was this very thick sludge production of 12 to 15% solids. And after thickening, this float could be thickened up to 35% solids. The final product here, this final sludge, is mostly FOG and potato byproducts. And the goal of this client was to minimize sludge disposal costs. And one option for him was to just take the final sludge and use it for animal feed. And that's exactly how the project turned out at the end. So a gem system was installed, treating their 4,500 meter cubes a day, with the final product being used as animal feed, using Veolia's Hydrex chemicals that are approved by the CFIA in Canada to be used as animal feed under certain conditions, which of course are met here in the current case. And then their sludge disposal costs was reduced to almost nothing, since the farmers out there would take this final product for free to be used for them as animal feed. Considering all of this, and without considering that the final sludge is used as animal feed, but doing a side-by-side comparison of operating costs and capital costs for the two options presented earlier, and considering $50 per meter cubes for sludge disposal in both cases, running with the GEM system rather than the conventional approach proved savings of more than $750,000 per year, plus some significant capital cost savings. This is based on a conservative assumption that no coagulant would be required in the conventional system, the conventional DAF and the lamellar clarifier stream, which was a very optimistic assumption, actually, because coagulant was most probably needed, but we could not run any lab tests to prove this strain. It was not part of our mandate. So even using this very conservative basis, comparison basis, there were still very significant savings offered by the GEM system. And then if you remove the sludge disposal cost of $50 per meter cube, which is shown here, the sludge cost, this block here, if you remove it, then the savings will be more than $1 million a year for sure. And it turned out that this client also found that it was a no-brainer to go with the DAF system. So in conclusion, the key takeaway message here is that the GEM system is a unique solution and is especially suited for the food and beverage industry, for effluents that have TSS and ideally FOG as well. Just TSS is okay, just FOG is okay. But of course, if you are a brewery manufacturer and you don't only have soluble CO2 in your effluent, then the GEM system is probably not for you. It does provide superior performances in terms of pollutant removal and generate very thick sludge in a very limited footprint. The good news is jar tests are very easily available, and we run them in-house in our lab in Montreal. And then piloting is also available, and it's written here piloting, but also rental if you want a temporary solution that can treat up to 160 meter cubes a day of wastewater. With that, TJ, I think you will take the poll here.
Yep, thank you so much, Danielle, for that presentation. Just a quick reminder for anyone on the webinar, there is a question chat box to the right-hand side of your screen. I'd like to welcome you to go ahead and type that question in there. We're going to try to get to as many as possible here. We already received quite a few. Just some other housekeeping items. There's some questions about receiving a copy of the presentation. Tomorrow, about the same time as now, you should receive an email with a recording of the presentation, so be on the lookout for that. And now we'll get to our questions here. Okay, the first question I have for you is what is the minimum pre-treatment prior to the gem process? Can you comment on that?
Yeah, good question. Minimum pretreatment is removal of the coarser solids, and actually in these mixing heads we have some orifices that do create a rotation movement of the wastewater, a vortex, and it does also generate some head loss. And these openings are probably the smallest points in the whole system. Ideally, we are asking for 1 millimeter perforated plate as a pre-treatment. In the larger gem systems, the openings are slightly smaller, larger, so we can maybe increase it to 2 millimeter, but that's the right order of magnitude, 1 to 2 millimeter. And then there's no requirement for sand removal or whatever else, so it's usually just this screening. And then equalization, pH needs to be at the right target number to allow the significant coagulation to happen. So it's really pre-treatment, which is this perforated plate screening followed by equalization with pH adjustment.
And a related question to that too is you talked about taking out some of those coarse solids and such. But is there any concern that you've seen when operating this technology with the LSGM heads becoming blocked due to the process or due to the solids entering in?
Yeah, this can happen, and usually is seen from time to time depending on applications. We have seen that lots of the food and beverage manufacturers do some packaging in one area of their plant, and usually these packaging operations involve using plastic material, and some shreds and small plastic particles tend to end up in their internal sewer network, and that will usually reach the wastewater treatment, even though they're not supposed to be there. These plastic material, you usually find them in any food and beverage effluent, and these sometimes will go through pre-treatment and reach the gem system. And if that happens, some of these small orifices can eventually get clogged or partially clogged. And so one thing that we are asking is to have some cleaning of these mixing heads. A typical, I would say, yeah, depending on application, it's very case specific, but a typical frequency can be once per week that you will open usually only the first head. That's where any coarser solids will accumulate. So, and then it's similar to basket strainer. You just remove the head, clean it, and put it back in, and then close back the mixing head. So that does involve some cleaning activity once or twice a week, typically, I would say.
And for a customer that might have an existing wastewater treatment process, could they use this in conjunction with a primary clarifier?
Of course. Actually, there's two folds to my answer. First thing, yes, if you have a primary clarifier, well, in theory, it should be doing what it was designed for, but maybe usually what you will see is the FOG removal is not great if you don't have if you don't have a good chemical conditioning upstream. So primary clarification may not do a very good job at emulsified FOG removal. So you could, if this is the problem, you could actually add a gem system upstream of the primary. And then your primary is useless, actually, because you'll get 95+% TSS removal. So your primary could actually become an EQ tank upstream of your gem system. Something else that we see, however, is people or plants operating a conventional DAF unit that is not producing satisfactory results, one thing we can do is to repurpose an existing DAF system into a GEM operation. So actually the separation tank with the surface skimmer is similar in any DAF system, including the GEM. So it's just a static tank with a skimmer on top. This could be reused, and we could come in and install LSGM heads, so the mixing heads, along with the feed pump and the air compressor and everything that's GEM related, and install it just on the side of this existing DAF system, which would be a retrofit GEM system afterwards. So you would actually be running a GEM system into your existing DAF unit.
All right, another question here for you is, do you need a sludge holding tank for storage of the fluid before thickening, similar to what is usually done with a conventional DAF system? Any comment on that?
Yeah, so answer is actually no. And you actually don't want one because there is this solids liquid separation that is happening quite fast. If you had an intermediate tank in between the thickener and the GEM system, you would have separation there. So actually you don't want a tank. And then that's one of the advantage of the GEM system. So you only have two components. You have the GEM and the thickener tank, nothing in between and nothing more. And then if you compare to a conventional sludge handling train, then you would need a sludge holding tank before your sludge dewatering system, which is not running 24/7. So you need this intermediate tank before getting to the dewatering system.
All right, some other questions that we have here, it's related to OpEx and also with the type of chemicals there. So can you talk a little bit about what kind of polymers you use, and also maybe even comment on some of the energy requirements to operate the GEM system?
Yeah, so in terms of energy, even though the GEM system is pressurizing the 100% of the feed flow, the first reaction is to say, well, this must be using quite a lot of energy. But at the same time, this feed flow is pressurized using a common centrifugal pump, which is running quite at a high efficiency, as compared to a whitewater recirculation loop in a conventional DAF system, where sometimes the self-aspirating whitewater pumps are very inefficient. So they're very useful, but not very efficient. So at the end of the day, the delta in the power consumption is not very significant between a GEM system and a conventional DAF unit. At the same time, if you look at the comparison of OPEX between different scenarios, you can see electricity here being the blue line, or that we have here at the bottom. It's never very significant when comparing two solutions, one involving GEM and one involving the DAF. You see much more cost in the chemical requirements. For this one, the difference was huge because we had no coagulant in the conventional DAF. If we go back a little in the other case study, in this one, then the chemical cost on the one end was here for the GEM system and much larger for the conventional DAF. Even we are using three chemical with the GEM system, so one coagulant and two polymers, while the conventional DAF systems are using only two. Usually it's one coagulant, one polymer. But then the coagulant dosage, when it's mainly, especially for emulsion breaking, can be quite significant on a conventional DAF unit using ferric or aluminum. In order to break the emulsion, the dosage will very fast become very high and eventually lower the pH significantly. So you may also end up having to adjust pH when you do your coagulation. And that's where the GEM system is quite efficient in terms of chemical dosage. This coagulant dosage, especially the organic coagulant, is very efficient at emulsion breaking. And so even though on a per kilogram basis, the organic coagulant is significantly more expensive than a metal-based coagulant, the dosages are much lower, which makes the whole chemical dosage cost quite competitive with the GEM system.
Okay, we're nearing the end. We have time for maybe one more question before we wrap things up. But a question would be there was some question about the application in various industries, and this one attendee was interested to know if this technology is applicable to the soap industry. So can you comment on that and maybe highlight some of the other industries outside of food and beverage where this technology can be applied?
So rule of thumb would be any effluent that contains oil and grease, fat oil and grease, is a good candidate for the GEM system. One very interesting and market for the GEM system, where there are lots of references, is in the metal processing industry, where oil is usually used for lamination, for example, of metals, which does generate a wastewater that is quite rich in oil and grease. And these are all emulsified oil and grease. So this is a very good application where the GEM can be used. Automotive industry, aircraft, manufacturing plants. So this generates effluent with FOG and emulsified FOG content. I can't comment on the soap application. It's an interesting one. I would say that the first thing I would do is to look into all the references and all of the jar tests that were done in the past to see if we have one similar application. At the same time, such a customer should contact us and provide us with more data. So what exactly is in this water? And at the end, if we're not sure, if we don't know, let's just run a lab test and we'll know the answer within a few days.
Sounds great. We got to most of those questions. There's a few that maybe we didn't have time to get to, so we'll try to circle back with you and engage you on those questions and make sure you get the information you need. Feel free to contact myself or Danielle if you have any more inquiries about this technology. So at this time, we're going to conclude today's presentation. I first want to thank our presenter today, our panelist, to share his knowledge about this really amazing technology. In addition to Danielle, I'd like to thank everyone who spent an hour with us here today to learn more about this DAF technology as well, the GEM. So if you, again, just want to remind you about the survey. If you take that survey, you'll be entered into a contest to win a $25 Amazon gift card. Thank you for that. And lastly, if you need anything else, please don't hesitate to contact Veolia Weather Technologies to get started on some kind of test or jar test or some lab test about your wastewater application. Again, thank you so much for your time. And this concludes today's webinar presentation. Have a nice day.